Well, dear friends, see in this lecture we will try to develop and strengthen our concepts through problems. So, see, there is one question. What here it is written. This is 5 liter container having N2, and this is 4 liter container having N2 with 2 bar pressure and 1 bar pressure. This time the temperature is different. Here 25 degrees Celsius and here 0 degrees Celsius. Means both were kept at a different thermostat so that temperature is maintained separately, and volume of this region you can consider negligible, and this is a wall. Now every part means this whole system is, you can divide in two parts. So this is the one part of the system having some different state and different state with respect to this part of the system. So overall this is a single system, but this single system is composed of different two systems with different state. So you have to consider this is a state, I mean one state of this system, and this is another state of the system, because temperature is different in both the cases, pressure is different in both the cases, volume is different in both the cases, and quantity is not given. So what is the need of the quantity, right? If you have 4 variables and 3 variables you are knowing, so very easily you can calculate the fourth variable. So there is no need to give you the fourth variable here. Right now, what they have asked, after opening this wall, definitely pressure is a potential. So whenever and which side pressure is more, gas will net flow from that side to other side, and whatever is happening. But finally in the whole system you will find the equal pressure. Means in here P pressure is same, here pressure is same. Initially it was P bar 1 bar and this is 2 bar, so let it be P bar here pressure, and this is the final pressure of this whole system. Now with respect to pressure, this is the single system. With respect to temperature, this is two different systems, because here see temperature is 25 degrees Celsius and here this temperature is 0 degrees Celsius. So this type of system you also may get. But since both the systems are connected, so with regard to the pressure, both are single system. But with regard to moles, with regard to volume, with regard to temperature, these two are different, right? So find the final pressure. Obviously find the pressure of final pressure of this whole system, and amount in terms of moles in 5 liter flask. So we have to calculate here how much moles of nitrogen are present here. We are considering in this region is negligible, right? There is no gas there and there is no moles of gas there. Okay, so let's do how to proceed. See, in volume, in terms of pressure, in terms of temperature and number of moles, the most faithful variable you can say that is the moles, because this will not change with change in pressure, with change in temperature, with change in volume. This will changes with itself. Means the moles of gas will change only when you add some moles to the system or you remove some moles from the system. Otherwise, moles will not change except chemical reaction. So here there is no case of chemical reaction. There is no case of cleavage of any intermolecular force, intermolecular bonds. There is no question of the change in the number of moles. So whatever number of moles here, number of moles of nitrogen here, and number of moles of nitrogen here, they are constant before and after. So we can write here, this is a hot part of the system and this is the cold. So with respect to temperature, I am differentiating these two systems, and before this and after this also, because there is nothing is mentioned in the question, so you have to consider this state is same before and after, means 0 degrees Celsius here, 25 degrees Celsius, still it is maintained. So we can write moles of nitrogen in hot part of the system plus moles of the nitrogen in the cold part of the system, means N hot plus N cold before opening. See, this is state 1 and this is state 2. So I am applying this in state 1, right, before opening the valve. So this is equal to, you can write, you can apply PV is equal to nRT in this region, plus you can add PV is equal to nRT in this region. So what is the pressure here? 1 bar, right? Means we can write here 1 bar pressure and volume 5 liters of this divided by R R 0.0 0.0821 liter ATM per mole per degree Kelvin, right? Okay, so this is what bar and liter ATM 1 bar. I mean here. So this I have to convert into ATM because here I have taken this ATM 8 to 1. So can I am giving you the value of R. R is equal to 0.08314, 0.08314. See, 0.0821 and 0.08314. This is liter bar per mole per degree Kelvin. So if you want, you can remember this 0.08314. So 0.08314 liter bar per mole per degree Kelvin, right? Plus 2 bar into 4 liter divided by 0.08314 liter bar per mole per degree Kelvin, and here temperature is 298 Kelvin, and here temperature is 273 Kelvin, right? So this is hot part of the system and this is cold part of the system. Now you can calculate, and if you solve this you will get this value 0.554 more, 0.554 more. Okay, so what I have calculated total moles present here and total moles present here. Sum of these two I have calculated. So this is the calculation before opening the valve. Before opening the valve, right? Now, consider after opening the valve. All of you are knowing that after opening the valve, after opening the valve, what will happen? There is transfer of gas from high potential to low potential, and finally you will have P hot is equal to P cold. Means pressure in the hot region is equal to the pressure in the cold region, right? So you can write here N hot. Now I am applying PV is equal to nRT here. Uh, uh, P hot is equal to N R T hot by V hot. This is equal to, we can write N cold RT cold whole divided by V cold. Clear to everybody? This is mechanical equilibrium. Mechanical equilibrium, right? Clear? Clear to everybody? Good. Okay. Now put the value N hot, right? So take it N hot, because this I have to calculate. So N hot R R cancel. T hot 298 Kelvin divided by V hot 5 liters. This is equal to, in place of N cold, we can write N cold is equal to 0.554 minus N hot. So we can write here 0.554 minus N hot into 273 divided by 4 liter. Okay. So when you solve this, you will get N hot is equal to your 0.296 moles. So this is one of the answer. Clear? Very simple concept. Only this is the concept required here, and rest is equation of state, PV is equal to nRT, right? Now P hot is equal to N hot RT by V. So this is equal to N hot is 0.296 moles multiplied by 0.08314 liter bar per mole per degree Kelvin, and 298 Kelvin whole divided by 5 liters. liter cancel, Kelvin cancel, per mole cancel. Right? So we will get the answer in bar. So the calculation of this will yield 1.47 bar. 1.47 bar. Right? So the pressure is here 1.47 bar in this region. And pressure here, what should be the pressure here? Same pressure. Right? So how this pressure becomes equal? So definitely the number of moles are different here, and volume is also different here. So accordingly, pressure will be fixed. So pressure of whole the system here and here, all the region, because now the whole system is a single system. Although with respect to temperature they are different, but the pressure becomes equal in both the cases, both the parts, right? So this is the concept of equilibrium, mechanical equilibrium, right? So this is the answer. 1.47 bar is the pressure after opening the valve and attaining the equilibrium. So this is the pressure in the 5 liters container, right? Now see another question. See, first read this question carefully, and after that try to solve this. The valve of the valve of a combustion cylinder of N2 gas was left slightly open so that a small amount of gas leaked. The leak rate is dP by dt is basically pressure difference. This is the fact. When you take some gas in the cylinder and if it is coming out, so definitely the leak rate is not directly proportional to the pressure inside the cylinder. This is always the difference of pressure of system and surrounding. So if pressure of this tank is gas inside the tank is more than atmospheric pressure, then the gas will leak out from system to surrounding, and if it is less, then from surrounding to system. The initial leak rate was this. See, this is very important point. Initial leak rate. Why this initial leak rate is given here? What is the role of this? So very important information regarding to solve this problem is this. And the initial pressure in the this meter cube tank was 180 kilopascal. What was the pressure of N2 in the tank after 1 hour? So basically, we left that container for 1 hour. Gas is leaking out, and it is asked that what should be the pressure after 1 hour. Assume ideal behavior of the gas and temperature 25 degrees Celsius and pressure 101 kilopascal. This is the pressure of atmosphere there, right? So how to proceed this question? See, first you have to find the expression leak rate. This dP by dt change in pressure per unit time, this is equal to minus K P tank minus P atmosphere, right? Why I have shown this negative? Because you know, every time after the initiation, pressure of tank gradually decreases, so rate will decrease, not increase. So this negative sign here in this equation shows the decrease in rate. So negative sign for decrease in rate, right? So every time once gas starts leaking, pressure of system will decrease, and therefore the rate will decrease, right? So minus K and this P tank minus this P atmosphere is 101 kilopascal, right? So dP by dt. So this is equation 1 dash, right? So here in this equation there is a constant K. So this, if we get this value of K, then the question becomes easy for us. We can integrate this equation between the time limit of 0 to what 1 hour, and accordingly we can calculate the ion pressure, right? So how to find the value of K? So next task is find the value of K, this constant. See, this initial rate, what is given here, that is useful to evaluate the value of K. Because once you calculate the K from the initial rate, definitely this K is constant over the time. So by using PV is equal to nRT, we can evaluate this K. See, PV is equal to nRT. So we can differentiate this dp with respect to time. So dp by dt is equal to, we can write d nRT by v by dt. So this is equal to, we can write RT by v. Why? The container volume of container is constant, R is constant, T is constant. So here we have dn, because moles of gas changing with time, dn by dt. But here see the rate is given in terms of what? Weight. See, initially grams per second, and here we have moles, so we have to convert this into gram. So n is equal to W by m. So we can write here, and molar mass is constant. So RT by m into V dW by dt. Right? This we can write, and this is equal to, we can write here what? Minus of K, P minus 101 kilopascal, right? So this is equation 2. So hopefully all of you are getting dp by dt is equal to this RT by m into V dW by dt. So I think all these things were known, so we can calculate here the value of K, right? So K is equal to, we can write minus RT dW by dt, right, by m into V P minus 101 kilopascal, right? So put the value here and calculate the value of K. So K is equal to minus 8 point, put the value of R 8.314 joules per mole per degree Kelvin. T is 298 Kelvin, and dW by dt, it is given what? Minus 1 grams per second. 1 grams per second minus, right, and okay, divided by 28 grams per mole. V is the 7 point what liter, 7.28 meter cube. 7.28 meter cube. And what was the initial pressure? Initial pressure was 17180. 17180 minus 101. This is kilopascal, right? So this we can put in the pascal. So into 10 to the power 3 pascal. Okay, so I think all the units, gram, okay. So everything I think will be cancelled out here. See, gram cancel, meter cube, pascal, so Newton meter square, and this per mole cancel, per Kelvin cancel, this joule will be cancelled, this meter cube and this pascal. So we will get per second. So what is the value of this? If you solve this, you will get 7.1 into 10 to the power minus 7 second inverse, right? So I think we have calculated this value of K. Very simple, right? Now again we can use this equation and integrate this equation. So dP by dt, dP by dt is equal to minus K P minus 101 kilopascal. So dP is equal to dP into P minus 101 kilopascal to the power minus 1 is equal to minus K dt, 0 to T, and P naught to P, right? P naught to P. So P naught is this here, and final pressure we have to calculate, right? So what is the integration of this? Integration of this ln P minus 101 kilopascal by this is P naught. So P naught is 17180. P naught is 17180 minus 101 kilopascal, right? This is equal to minus kT. So this is equal to minus K. K is 7.1 into 10 power minus 7 second inverse into 1 hour means 3600 second, right? So solve this, solve for P. P is the final. P naught is 17180, right? So solve for P, so you will get P is equal to 17140 kilopascal, and this is the answer. So in this way you can solve such type of problems, right? See, this is log base e, so you can convert 2.303 log base 10 for the calculation purpose. Then you will get this final answer, right? So now you can solve this equation, and solution of this equation you have to, this is, you can assume your homework, right? So this is homework. So solve for P the above equation, right? Okay, so in this way we can calculate the pressure after 1 hour in the cylinder, right? So this is the way how to calculate such type of problems. Okay, now see, payload capacity, we will develop some concept. Payload capacity of a balloon, right? Payload capacity of a balloon. Now see, first we will see what is the definition of payload. See, payload is basically defined as for balloon, or this is also used in the missile technology. This terminology also used there. So payload means additional weight, right? Not total weight. Additional weight. What is meaning of payload? So the additional weight along with any balloon or any missile can lift in air. So additional weight. There is some weight of balloon also, some weight of gas inside the balloon also, right? But along with that mass of gas inside the balloon and this mass of the balloon, whatsoever additional weight that can be lifted by any balloon is known as payload capacity. So payload capacity is defined as the additional weight, the additional weight along with any balloon can lift in air, known as payload of balloon, right? So we can say payload is equal to Archimedes principle. You can use mass of air displaced minus mass of balloon plus mass of air, mass of gas inside balloon, right? So this is the simple formula of payload capacity, right? Simple formula of payload capacity of any balloon. So sometimes if mass of balloon is not given, so don't consider that mass. Don't put from your side that this the material through which balloon is made up of, that mass is this. Sometimes examiner may ignore that mass, so you can ignore also in this formula. And mass of air displaced. How to calculate mass of air displaced? So mass of air displaced is equal to density of air into volume of air. And what is the volume of air? Volume of air is the basically volume of balloon, right? So this is the density of air multiplied by volume of balloon. Balloon. If it is conical, if it is spherical, so accordingly you can put the volume of balloon. So in this way you can calculate the mass of air displaced. And how to calculate the mass of gas inside the balloon? So for that you can use equation of state. So mass of gas inside balloon is equal to PVM by RT, where P is the pressure of gas, V is the volume of balloon, M is the molar mass of the gas, R is the gas constant, and T is the temperature. So mass you can calculate by using this, right? So P is the pressure of gas inside balloon, V is the volume of balloon, M is the molar mass in kilograms per mole, don't write in moles. Similarly, accordingly, you can set the units, right? Molar mass of gas in kilograms per mole, and R and T. R is the gas constant and T is the temperature. So in this way, you can find the mass of gas, mass of air displaced, right? So this is the way to calculate the payload capacity of what balloon, right? Well, see, this is a example based on the above concept. What will be the volume of helium needed in a balloon to lift 1 kilogram mass? Assume the temperature is 25 degrees Celsius, which is constant, and pressure is 1 bar, which is also constant. And see, molar mass of air, average molar mass of air, this is 29 grams per mole. This is given. And see, this is, almost constant, so don't worry. So see how to proceed this. Payload is given here 1 kilogram. So payload is equal to mass of air displaced minus mass of balloon plus mass of helium. See, mass of balloon is not given here in this question, so you can take 0 this. So this is basically mass of air minus mass of helium. So neither density is given here, nothing is given. So we can modify our approach of calculation. Mass of air is equal to, we can write here, moles of air into molar mass of air minus moles of helium into molar mass of helium. We can use this. Just manipulation is required. And you know what we can write here, that the moles of air is equal to the moles of helium. How we can write this? See, what is the volume of air displaced? Volume of air displaced is equal to the volume of balloon, and volume of balloon is the basically volume of helium. So volume of balloon basically the volume of helium, temperature pressure constant, so we can use this volume is directly proportional to the number of moles, Avogadro's law. So I have applied here Avogadro's law, so we can write this moles of air is equal to moles of helium. So this is equal to N, we can write here, and molar mass of air minus molar mass of helium. Now your question solved. In place of N, you can write PV by RT into molar mass of air is 29 minus 4. So this is equal to PV by RT multiplied by 21. 25 grams per mole. And this is payload is given 1 kilogram. So from here you can calculate the volume of what? Helium, right? Basically this volume of helium is equal to the volume of balloon, right? Because pressure inside the balloon and outside pressure, that is 1 bar, that is constant, right? So from here you can write volume of what they have asked, volume of helium. Volume of helium is equal to the volume of balloon is equal to the volume of air displaced, right? So volume of helium is equal to 1 kilogram into R, value of R we can put 8.314 joules per mole per degree Kelvin, and T is 298 Kelvin divided by 1 bar. 1 bar they have given, okay, 1 bar multiplied by 25 into 10 power minus 3 kilograms per mole. Kilograms per mole, right? So we can solve this. So we will get 0.99 meter cube, right? So this is the answer. So this is another way to manipulate mass of air and mass of helium in terms of moles, you can simply manipulate this. This is also acceptable. And this formula, when you have density and volume, all these things are given, then you can use this formula as well, right? So in this way, you can solve such types of problems. Similarly, some temperature difference also you can find out in terms of payload capacity, that also you can solve, right? So if a question will come that what temperature difference is required, so in the same manner you can put the value del payload is equal to mass of cold minus mass of hot, and in this way you can put P is equal to nRT and calculate. So similar question you may get in your module and in your exams as well, right? Now see one more question. This is very good question. In fact, see, the average molar mass of the vapor above the liquid acetic acid is 101 grams per mole at 1.01 bar and this degree Celsius. Okay. Assuming that a dimerization reaction occurs, determine the partial pressure of monomer and dimer in the vapor phase. See, first all of you should try to understand what is given in the question. See, suppose that this is a container in which liquid acetic acid is there, and all of you are knowing that this CH3COOH and vapor in vapor phase, when acetic acid molecules are in equilibrium with this liquid phase, this is a liquid phase and this is the vapor phase, right? So in vapor phase, this acetic acid molecule dimerizes through intermolecular hydrogen bonding. So the question is given that 2 moles of this, they were dimerizes in this manner. OAH, CO, CH3, OH, and, right? So this is a dimerization reaction. So this is monomer, and this is dimer. So this average molar mass is given for this vapor phase, not for this liquid phase. So all of you are knowing that the average molar mass is equal to sigma xi mi, right? Where x is the mole fraction and m is the molar mass. So average molar mass, this m is given for this mixture, and that is 101 grams per mole. This is equal to this x monomer and dimer both were present in the vapor phase. So x of monomer into molar mass of monomer plus x of dimer into m of dimer, right? So x of monomer, x mono, and molar mass of this is 60 monomer grams per mole plus mole fraction of dimer into 120 grams per mole. Grams per mole, grams per mole, grams per mole cancel. So here 101. So you can you can write here 101 is equal to 60 x monomer plus 120 x dimer. This is equation 2. And one more equation we can write, that x monomer plus x dimer is equal to 1. So we can write here x monomer is equal to 1 minus x dimer. So from equation 2 we can write here 101 is equal to 60 into 1 minus x dimer plus 120 x dimer. So this is equal to 60 minus 60 x dimer plus 120 x dimer. So 101 minus 60 minus 60, 41. So we can write here 41 is equal to 120 x dimer minus 60. So this is 60 x dimer. So x dimer is equal to 41 by 60, right? 41 by 60. So this is 0.68, 0.683. So x monomer is equal to 0.316. 0.3. So we have calculated mole fraction of monomer and mole fraction of dimer. Now see partial pressure of monomer and dimer. Partial pressure of dimer is equal to mole fraction of dimer into P total. So mole fraction of dimer is 0.68 into P total is 1.01 bar. So this is equal to 0.68 multiplied by 1.01, 0.68, 686 bar. And partial pressure of monomer is equal to x of monomer into P total. So this is equal to 0.31 into 1.01. 0.31, right? So it is 0.31 bar, and this is 0.686 bar. Right? So in this way you can calculate this. So this is I think I have considered all variety of questions based on PV is equal to nRT and Dalton's law of partial pressure. Right? Now I will take up the next topic, that is kinetic theory of gases.